So we started the recording, so the recording is now started. So, alright, we're gonna look at, as customary, we usually look at the cross outline to see where we are and to also look at the labs to see how far we reach at the labs. And I take it that everybody finished the assignment. Mhm.
Which one of the assignments, sir?
Digital assignment, digital electronics assignment.
Which one that? Remember, cause we do so much assignment. Sometimes we
All
have
right,
miss.
so let me just share. Let me just share my screen. See this one right here says 7 turning. So let me look at the 7 person who turning. I will look back at the assignment. So Roger turning, Barrington turning, Kenzo turning. So Palmer don't turn in anything yet. So Palmer, Palmer.
Yes, sir. Yeah, hear
Yeah,
me?
yeah, yes,
Yeah.
yeah, yes. So you need to
Me
turn
never
in your
see
one.
pop up. I don't see it come up on my section.
You don't see it come up on your section. You have the Google Classroom code for
Yeah, I'm
digital
in there.
electronics. Alright, look right here. So it's the assignment.
All right, hold on.
Mhm,
Me I go on it right now.
mhm.
Cause normally I would have get an email for the assignment.
Oh, so what you do? Just upload the same place right here. So we take it. Same place right here. You're gonna upload it back same place here. When you're finished with it.
All right, so I'm in the digital electronics
Yeah,
class.
yeah. Look for assignment. Go on classwork. Don't stay on stream. When you stay on stream, it will look something like this, and it's more difficult to find it. But when you go to classwork, like
And I
right
go to
here,
assignment.
right, you see assignment right here,
Okay, all right, I
and
see it now.
these are the lecture notes and everything. So everything is there. Right. So we're gonna look at the course outline, and then we see where we are, what we have covered already, and where we need to go. So cover most of these already. Um, Unit 1, Unit 2, Unit 3, we are doing others and subtractors. So we need to go to counters and registers now, but we need to finish up this part of it, which is the subtractor, encoder, decoder, multiplexer, and the multiplexer. So we're gonna see if we can do all of this today so that we can go and flip flop in the next class. So let's just look at something on the lab first before we go further again. So the lab. So according to the lab, it's a instruction for all labs. So for all labs, they must do this. Use electronic workbench or multisim for a schematic diagram. And you're gonna use Tinkercad for integrated circuit simulation. And then you're gonna construct it on an actual board as a prototype. So when you come in, you're gonna put it on an actual board. You'll do the schematic diagram first using the electronic workbench or the multisim, and let me just remind you how that's supposed to look. Right, so let's say for instance you have a logic diagram right here. These are some virtual ICs, but you're gonna use a virtual IC when you're doing you're not gonna connect them right. You're gonna use Tinkercad to connect it. I don't want to connect do this using IC right here to connect it. Right, so you're not gonna use this one to connect it, but it's got you want to do some schematic, and to do the schematic diagram you're gonna use things like this. So this is one of the gate, which is a NAND gate. So when you are connecting this NAND gate, this would be, for example, a schematic diagram. Looking for a single pole, alright, here's a single pole switch, single pole, single throw, which is this one down here. Single pole, which is SPST, single pole, single throw. So I want to use those switches. I'm gonna use two of them. One for each gate. So let me just move this out of the way. And I want one to be A, I want to be B. So I want this to be A. Let's just key A. S1. Okay, I'm change this as well. A. Let me just take off one of them. This one refused to go, so we're gonna take off this one. Alright, it refused to go, so I'm gonna have to just keep them. I'm gonna keep both of them. So now that one pin is A and one pin is B. And that's as simple as what it is saying. Alright, we're gonna join both of them around there. I'm gonna put on grounds. So I want to use a negative ground. So this would be a schematic diagram. And I want to put an output on it, so I'm gonna just put a regular, can even put a probe on it in the form of a LED. And we can use the different colors that we want. Any color LED we can put on. You can choose to let the color be whatever we want it to be. Let's replace properties. So I want it to be either blue or red or one of those. We're going to choose the blue. So if we run it now, we know that both pins are off, and this is a NAND gate. Right, and we're supposed to have it come on at a certain time or under certain condition. Just a minute there. Alright. Look like, hold on, look like something wrong there. Hold on. When I run it, it's supposed to. When it is off, when both gates are off, I'm supposed to have it on right now. It is not on. I don't know why it's not on. Run it again and see something. I don't know what's going on there. So what's going on here today? Why it's not coming on? It's supposed to come on, man. So, if the multi-sim is not working, cause right now I don't know why it's not working. Let me just try deeds. Cause usually I use these as well for the. I don't know why it's not coming on using multi-sim. But if the multi-sim is not using, use this for the to the schematic diagram. Usually these has an advantage over most of these simulation are simulated. So we're gonna just use this one. We're gonna use the same gate that we used a while. To input AND gate, NAND gate. Alright, so I'm gonna put two inputs on it. And I'm gonna check out why it's not working in the multi-sim. I don't know why it's not working, but it's supposed to work. Yeah, maybe something is wrong with my multi-sim. If I run it like up here, let's see a bit. It is both pins are off. It's supposed to be on, and that's what's supposed to happen right here with this. Cause both pins are off. This is supposed to be on, but somehow it's not coming on. Because when it is on, it's supposed to look something like it's supposed to have something like it is glaring, but somehow it's not coming on. I don't know what happened, why it's not coming on. But this is how it's supposed to set out in the multi-sim if you are doing it in the multi-sim. If you are using electronic workbench, which is a other electronic simulator, let me just go to it and see what would happen with the electronic workbench. My electronic workbench is giving some trouble on the simulator. I see right here, it is giving me something right here. Alright, let me try it again and see. Something is wrong. Probe do not plot to the graph for interactive simulation. Okay. Let me just change up this probe. Put something different. Alright. This is saying 100 volts, so that need to change. And this is 6 volt right here. And we can't put too much volt on the logic gate as well, so we have to bring this down to about 5 or 6 volts. It's still not doing anything. It's supposed to be moving, but it's not moving. So I'm gonna have to check out what is happening to my multi-sim, because it is giving me some error down here as well, which shouldn't be. So I don't know if it's changed. It want to change, or because it's a trial version, they don't want to, and the time soon expire. They don't want to give me any any more try out of it. So anyway, if your simulation is not your electronic workbench or the multi-sim not working, just use the deed and show the schematic diagram, because this is a schematic diagram. Alright, also what you need to show, so you can use the electronic workbench multi-sim, and I should kind of write in your deeds. So on your thing, just put deeds, because this can be used right here. So use electronic workbench multi-sim or deed for a schematic diagram, and then you're gonna use Tinkercad for an integrated circuit. So let me show you how that works. I think Tinkercad is an online simulator. So if you don't have an internet, it's not gonna work. So you have to have the internet for it to work. And it is not really downloadable. Just a minute. Because I want to make sure that everybody on the same page when they're doing the lap them. This is taking a little while. Why is this taking so long to come up? Sometimes I give a little trouble when I try to log into it. Give a little trouble like this. What's going on here now? Alright, start tinkering. Alright, let me try that one here now. See? It came back same place. It's not supposed to come back there, someone. And not any giant class business. Let me see if I can oh Lord, man. Now give me what I want, man. Let me just come out and go back into it. What's going on here so they think I can today? Came back same place. Let me try this to see what can happen. Alright, so I can use this one right here, so. It came around. This is what is sometimes, you know, it just came around and round and round and round and round all over the place. Alright. So if I want to use the IC to do it this way now that I wanted to do it, let me see, go back to classroom. Right, so we're gonna use Tinkercad for integrated circuit IC simulation. So we're gonna do the integrated circuit. Integrated circuit is the same thing they call it IC. So IC means integrated circuit. So we're gonna look for IC, for logic gate IC, just like how we do it in these are the multisim. Remember now this is schematic diagram, so you're gonna do it like this is schematic diagram. Then you will do it like what we have in the Tinkercad. So we're gonna look for a logic gate. We're gonna look for a NAND gate. This is a NAND gate right here. Alright. And when we look up this NAND gate right here, so 74HC00. So we can look it up on the internet and we see where all the pins are. Or we can just look at it and we see where the pins are. This is number 1 right here, so we can tell if it's our input. This is our input right here, so input A, input B, and this is our output 1. So this output is for this and this. This down here so is usually the ground, and this over here so is usually power. So I'm gonna put the power up here. I'm gonna put the grounds right down here. And we usually use a negative for the ground. We usually use negative ground. Most of the time we use negative grounds. So we're gonna use this small battery right here. I'm gonna put the power on it right away. Hold on. I don't want to do it this way. I want to bring out a breadboard and do it on the breadboard. Alright. So
So I want to go on this where you connect the positive and the two positive.
alright. No, this not supposed to be in the positive, it's supposed to be in the negative. So
Okay.
that's supposed to be there. Yeah man, thanks for that. Yeah man. Alright. So we know that we can, so all of this right here is negative, so we can put on a negative right here from here to here because it connects here on the ground, don't it? Negative ground. And we can bring on the battery now, the battery positive. Can bring on this positive right here to this right here, so we can connect this to this. So right away it connect to the positive, don't it? Everybody see that? Hello? But not talk. This is positive right
Yes,
here.
sir. After you have to go on.
Sir,
this-
remember that
this
I'm
is the
driving,
IC.
sir. Remember that I
Okay.
told that I'm driving.
Right, and this is the IC right here. The IC is positive, so put the positive leg right here. Remember we're using the 3 volt.
So going down, you connecting a one as a series going down and not across.
And not across. And the reason why I put it like this, no, let me just put back this IC up here. Right, so the IC now is across a bridge. The IC now is across a bridge. No, the IC is now across a bridge. So you realize that nothing right here is connected. Only it is connected in vertical, but it is not connected horizontally. Same thing with this here, so it's not connected horizontally. But if I click right here, so I can put anything at all right here, so for pin 1. So I'm going to put a switch for pin 1, yeah?
Yeah, so where the input there, and that's where the positive is supposed to be.
No, man. This is the input. Right here gonna be one of the input, and this is gonna be the next input, and this is the output. I see it right here, so input A, input B, and output 1.
Output.
Alright?
Okay.
So we're gonna put in the 2 input first. I'm gonna use 2 switches for the 2 input. So we're gonna use 2 switches for the 2 input. Alright? So, alright, we have 2 switches. We're gonna use this one. Alright, so here's the thing now. You see this command pin right here? Let me create up further a little bit. You see this pin right here, so it is the command, the middle one. Right? So I can use any one of these on a pin, terminal 1 or terminal 2, terminal 1 or terminal 2, but I have to use the command pin. The command pin must have to use. So I'm gonna put the battery on the command pin, which is the positive. I'm gonna put the positive on the command pin. Right? So because the command pin is right here, I'm gonna put this command pin and this command pin together. So I'm gonna go up like this to meet right here, and then I can go across with it over here. Everybody understand that? What I'm doing? Alright?
Yes, sir.
Yeah. So right now I put a positive on the command pin. Now I want to put in the input. Now I want to put in the first input. So this first input, which is this right here, I can put it right here, don't it? Let me say it again. We can use either terminal 1 or terminal 2, but we're gonna use terminal 2. We don't have to use the two terminals. I don't have a single pole switch like this one. Like this one, where it does have two terminals. The one that we have is a 3 terminal. Let me show you how that would look. It's a double pole. Let me show you how that would look. A single pole double show. Right. So the one that we are working with is still like this. It's a single pole, but it has a double show. We can use any one of them to turn on and turn off something. If we're using this one to turn off and turn off something, we use it alone. If we're using this one alone, we use it alone. But this is the command right here, so this doesn't change. The command is the one that varies. That go between pin 1 and pin 2. This one does have 2. So it's, see still like this? See it? So this now, this can let's say first time we're using this part alone, just like how this down here so stay. This can lock off and turn on, we're just using these 2 pins. We can use just these 2 pins alone. We don't have to use this one right here. We just use this, we just use this. Everybody understand that? We don't have to use the one here to do it.
Yes, sir. Yes, sir. Understand.
Right. So it's the same thing now with this. This is the command right here. So we're not gonna use pin terminal 1 or pin 1. We're gonna use pin just the command on pin 2. Same thing with this, we're gonna use the command on this and pin 2. Alright. So we're gonna take from this now. I'm gonna carry it across to terminal 1. Then I'm gonna use this one right here and carry it across to this right here. Everybody get that? This line up right here, so you know, so it line up to this, don't it? This is one of the inputs right here.
Yes, sir.
Alright. And where's the other one? See the other one right here? This line up to the next input, don't it? But this is the output now, so we need to get a bulb and get something for the output. So we're gonna get a LED for the output. So we're gonna use an LED right here. But when you use the LED now, the LED has a cathode and an anode. The cathode is the negative side and the anode is the positive side. So let us see if we can spin on this right here. Right. So I want to get this part, the cathode, connected to the negative terminal. Right? Because the cathode is always connected to the negative and the anode is always connected to the positive. But in this case, I want to put the anode on the output. Right, so we can come right here and we can go across right to the output right here. But see that? So this one is connected to the output, but this one must connected to one now. The negative, don't it? So you can pick it up from right here and carry it. Either we can either cross right here or we can carry it right down here to the negative. Right, and we'll just label it up. Alright. And we can run it now to see what would happen. Alright, there it is right here. So both of them are off. So it would come on. You see it?
Yes, sir.
Alright, so if you look at the truth table for a NAND gate, look at the truth table for a NAND gate and tell me how the NAND gate work. Now, give me the truth table for the NAND gate.
Sir, basically with the truth, you want me to tell you how the truth table work for the NAND gate?
Yes, the output, give me the output.
Alright, the output, alright. What should I do? The 0, 0 and the
output.
1, 1?
Yeah, the 0, 0, 1, not the input, you know, because we know that the input is 0, 1, 1, 0. So if it is A, B, and the output is C, then we know that it is 0, 1, 0, 1, 0, 0, 1, 1. That's the two input.
Right.
Right? And for the output now, what you're supposed to have now for the NAND gate. If
I
it
think
is,
alright,
if
zero
everything
zero
is
zero.
off, if everything is off, we should get 1. All right. And if you just have 1 0, if as long as you have a 0, you're gonna get a 1. But if you have 2 1s now,
You're gonna get 0.
you're gonna get 0. All right. So we're gonna try that. So right now we have 2 zeros, two half. So we're gonna get a 1 out here, don't it? So we're gonna trouble one of them and see what happens. It remains, don't it? We're gonna trouble this too. It's supposed to remain, don't it? But when we turn both of them on now, both ones, it is off. And this is how you connect up the simulator for the NAND gate. Now, we're not doing it on the actual circuit board now. Let me just go to it back again now. Back to the classroom. So I'll show you how to do it right here. So either you're gonna use the electronic workbench, the multi-sim, or the deeds for the schematic diagram. Then you're gonna use the Tinkercad for the integrated circuit IC. That's what I do look a while. Then you're gonna do it. You're gonna come in. I'm gonna construct it on an actual breadboard as a prototype. And when you come in to connect it as an actual prototype on the breadboard, this is how it's supposed to look. Just like how you have it on the breadboard, that's how you're supposed to have it. Just like how you have it on the Tinkercad breadboard, this is how you're supposed to have it on the actual breadboard. Because I want to see if you can really do it. I'm going to take picture of everything. So you're going to take picture of the one that is indeed, and I don't want to see anybody one looking like my one exactly. You're gonna take a picture of this one as when you not do it, and then you're gonna take a picture of the actual one when you come in and do it. We have a lot of switches that you can use, some single pole, single show switches that you can use to do the simulation. Alright, so let me just show you something again we need to do. Now, for each lab, which is all the lab them, you're gonna do a documentation using APS 7th edition. Right? In the document, you're gonna define each lab or circuit or logic gate. You're gonna do some definition right here. Then you're gonna explain the operation, including truth table. Right? And then you can tell where you can apply them. Right? And for lab 1, you're gonna draw 3 basic logic gates, the 2 universal gates and 2 specialized gates. We know the 3 basic logic gates. What are they again? What are the 3 basic logic gates?
You have AND.
Yes.
You have OR.
Yes.
And you have NOT.
NOT. Those are 3. All right. What are the 2 universal gates?
The XOR gates. The XOR.
No.
Sir.
Two.
Sir, the X.
No.
X.
No.
X NAR.
No. The universal gates are the gates that are that work with the NOT gate and the NOR.
The NOR.
And the NOR. Right.
Yes.
And the specialized gates them. What are the specialized gates them now?
The XOR gates.
XOR, and XOR, XNOR and XOR. All right. So you're gonna draw the truth table for each gate. See how simple this is? You're gonna draw the truth table for each gate. I'm gonna write the Boolean expression for each logic gate. This is very, very simple, don't it? Are you reach far now? So this is supposed to be ABC now, don't?
Sir, repeat please, sir.
Alright. So you're gonna draw the 3 basic logic gates, the 2 universal gates, and the 2 specialized gates. So how many gates in all you're supposed to have?
Sir.
How much? How many?
7, because the 3
7.
universal.
Right, exactly.
Yes.
And for each gate, for each of them, you're gonna draw the truth table for each gate. You know how to write the truth table for each gate, don't it?
Yes, sir.
Okay, alright. I'm gonna write a Boolean expression for each logic gate. That easy.
Yes, sir.
Give me an example for the AND gate. How do you write the AND gate using Y as the output?
Oh, you like that the AND gate using wire output?
Yeah. Y as the output and A and B as input. How do you do that? A is equal to. Sorry. Y is equal to A
Y
and
is equal to A plus B.
no, not plus. It's a hand, no. It's a hand. The plus
Oh,
is
is
a
the
R.
AND?
Yes.
That the dot.
Yes,
The dot
exactly. Y is
B.
equal to A dot B. R A and B. All right. What about this now, which is number 2 now in lab 1? All right. So you're gonna look at this circuit up here. I'm gonna draw the truth table for the circuit. So you must draw the truth table for the circuit right here.
Yes, sir.
All right. So good. You're gonna write the Boolean expressions for the circuit above. You must do that. So this and this you're gonna write out. Use K map or corner map to simplify the Boolean expression. You're gonna convert the expression using the Morgan's law. You're gonna write the sub and the post expression in conical form from the truth table. Alright. Given the expression below, this is supposed to be 3 right here. I don't know how this end up with 2. It's supposed to be 3. Alright, given the expression below, which is this right here, so draw logic circuit using appropriate gates. So you look at this and tell what type of gates right here, so how many input or gates you're supposed to have right here? You're supposed to have an OR gate right here?
Yes, sir.
Alright,
Two
so work that out, alright? Next
Two
one,
of them,
write the
two
truth
of them,
table for the expression. I'm not telling you. Write the truth table for the expression. Alright, so this is the expression right here. I'm gonna develop a truth table for it. Alright, lab 2. Draw a full other circuit. We must do that by now. Draw a truth table for other circuit. Write the expression for the full other circuit. Draw a full subtractor circuit, which we're gonna look at right now. Draw the truth table for a subtractor circuit. Write the expression for a full subtractor circuit. Then number 3 now, flip-flop. And flip-flop are the basic building block of computer memories. Like RAM and ROMs and registries. The flip-flops, that's what we use to hold information, to hold bits and bytes, right? So we're gonna go on this next week. So lab 3, you can start lab 3 next week, but I expect you to start lab 1 and lab 2. But we're gonna look at the subtractor circuit now, 2 subtractor circuit, and we're gonna look at the expression and so forth on it. Alright, so here we go. We're gonna go back in the classroom for the subtractor circuit. See, subtractor circuit is right here. When you look at the half subtractor, they will look at the full subtractor.
In this class, we are going to discuss.
As we go along, we will explain. So when we talk about combinational logic circuits, we're talking about circuit like this, where we use different logic gates. As long as you use different logic gates, or use more than one logic gate to create a circuit, it is called a combinational circuit or a combinational logic circuit, because you combine various logic gates to make it, right? So a half subtractor is a combinational circuit used to get the difference between 2 single bit numbers, right? So these are 2 input, 2 single bit numbers. We can put in any one of them, and we can get the difference at the output.
In this class.
Oh, by the way, just like how the other circuit has a carry, what do you expect the it has a sum and a carry? What do you expect the subtractor supposed to have? What is one word that you can use when you're talking about when you're adding two values? What do we refer to the output as? The sum, don't it? Hello.
Yes, sir.
All right. When we're doing multiplication, what do we refer to the output as?
Product.
All right. What about division? Quotient.
Yes,
all right.
sir. Quotient.
All right. What about subtraction? Difference. Got it? Yeah, man. We're not doing subtraction. Okay,
Yes, sir.
difference. All right.
Yes, sir.
So for the subtractor circuit, just like how we had for the addition circuit or for the other circuit, we have sum and carry. For the subtractor, we're gonna have difference and borrow. That we're gonna have to borrow from one side to put it on the other side, don't it? Don't you do subtraction, you know, borrow from something, don't it?
Yes, sir. Yes, sir.
So that's exactly what we're gonna do right now. So we'll be doing that right now.
In this class, we are going to discuss about half subtractor. So similar to half adder, this is going to subtract two single bit numbers. So here see the definition of half subtractor. Half subtractor is a combinational circuit used to get the difference between two single bit numbers. Here this is the block diagram of half subtractor, which is having two single bit numbers as input and two outputs. Those outputs may be difference and borrow. We know that when we are subtracting two binary numbers, sometimes we are getting borrow. That's why we need to consider borrow as one output for any subtractor. So here, to design this functionality as a logic circuit, we need to consider truth table and then K-map. After that, by using expression from K-map, we are going to consider the logic diagram. So for this, as this half adder is having two inputs, so I am taking two inputs in truth table also. Two inputs and two outputs. So here for two input variables, we may have four combinations. So that four combinations, you already know that 0, 0, 0, 1, 1, 0 and 1, 1. These are the all possible combinations.
If you don't remember that, just say 0, 1, 0, 1, 0, 0, 1, 1.
With two input variables. Now for the functionality, which functionality we need to discuss here means subtraction. So here the subtraction between A and B we need to consider. So here if you are taking difference between 0 and 0, that is normal arithmetic subtraction, what you are going to get means 0. 0 minus 0 is equivalent to 0 only. Are you hearing any borrow means? You are not hearing any borrow, then you need to put 0 in borrow place. So now you need to consider difference between 0 and 1. So 0 minus 1. In normal subtraction rules, 0 minus 1 means 1 with borrow 1. So here difference is 1 and you need to consider borrow 1 for that difference. So here 1 minus 0. In normal subtraction rule, 1 minus 0 is equal to 1 only. There is no borrow. So here you are having 1 and no borrow here. And 1 minus 1 is equivalent to 0. You are not hearing any borrow in this case also. So just put 0 in borrow case. 1 minus 1, it's equivalent to difference equivalent to 0. So now you got your difference and borrow, which are the outputs of a half subtractor. Now you need to consider the K-map for both difference and borrow to get the logical expression. So
alright, so I hear it in somebody's mind, how do we do subtraction of binary number? you have to go back to what we did originally when we're doing that part of the course. So let me just refresh your mind and give you something like that for you to understand.
Subtraction. This is like in this class we are going to discuss binary subtraction. This is like general subtraction only. Binary subtraction means subtraction between two binary numbers. So here this topic is also under
And it has a little trick to it where you have to understand.
Binary arithmetic. Here this binary subtraction can be done by using some rules. Here we will see what are the rules for binary subtraction. For example, if you are subtracting, these are the rules for binary subtraction. For example, if you are subtracting 0 from 0, you are going to get 0 only. This is the first rule. And second rule, for example, if you are subtracting 0 from 1, you are going to get 1. This is second rule. And the third rule is, if you are subtracting 1 from 0, that means 0 minus 1, then the result is 1 with borrow 1. So this is the result when you are subtracting 1 from 0. So the result is 1 with borrow 1. So
alright, everybody understand this, people? Hello?
No, not really, no, sir. Sir, not really.
Alright, we're going to go in detail. She's going to explain it and then I'm going to explain it again after. So it is 0 minus 0. In normal subtraction, we know it's 0. Boolean algebra is the same thing. 1
Sir,
and minus 0, you're going to get back your 1. Right? Whether you do it in normal subtraction or binary, same thing. 0, no minus 1. This is the only trick in the whole entire thing of it now. 0 minus 1 equal to 1 with a borrow. And she's going to explain the rule and then I'm going to explain it again for emphasis. Right? So this is the only one that you need to concern both. 3 rules. This rule regular, this one regular, but this one has a little trick to it.
So subtraction result is 1 and borrow is 1. Here we are not calling this as carry. In case of subtraction we have to call this as borrow. Now here last rule 1 minus 1. If you are performing any 1 minus 1 operation, then the result is 0. So based on these 4 rules you are going to perform.
So this is regular, this is regular, and this is regular. This is the only one that you have to concern with.
Some subtraction operation. Let me take an example to explain this. I want to subtract. So subtract some 0, 0, 0, 1, 1 binary from 1, 1, 0, 0 binary. These two are two binary numbers because you can see the base here. These two are two binary numbers. The problem is to subtract this particular binary number from this number. So that means the problem given is 1100 minus 0011. Like simple subtractions, you just.
Everybody understand that so far? Because usually student tends to misunderstand when they write it out like this. So it is this. You're gonna take away this from this. In other words, it is this minus this. Everybody get that? It is this one over here, this one minus this one. So when I say this from this, it means that this gonna come from this. You're gonna take away this from this. In other words, this one, this binary number from this one, from this one. this is the bigger one. This is the smaller one. So you're gonna take away the smaller one from the bigger one. Don't want to get any negative.
Just take like this 1 1 0 0 one after another. So you just consider like this. So here see the rules. 0 minus 1 means, so here the result is 1 with borrow 1. So where we have to get that borrow means, here you are not having any 1 to get borrow. So here see the next place, you are having 1. From that one you have to take borrow, and here the result is 1 with borrow 1. So whenever you are taking this 1 to this side, it leaves borrows on the middle zeros. So here you are taking so 0 minus 1 means 1 with borrow 1. Here you are subtracting 1 minus 1 here. Here you are having 1 right now. So now,
alright, so
now 1 minus 1.
Let me ask a question right now. Like how this is take away, right? I put it over here, so this one right here is gonna be right here. So what gonna be right here now? So we take it up, we take it away. So this gonna be what? A 1 or a 0? If we borrow it, it can be 1 again. Don't it? Can we carry it somewhere? So if we take it and borrow it and carry it somewhere, then it's gonna change. Everybody understand?
Is equal to 0. Here this 1 is given to borrow for the first bit, given as borrow for the first bit. So,
oh, and by the way, this one right here says 1 minus 1.
there is nothing now. So 0 minus 0 is 0 now, and here you are having 1 as it is here, and 1 minus 0 will provide you 1. This is the simple subtraction result of this.
Alright, you have another way or you could do it as well too. Changes into decimal numbers. Alright, so we're gonna change it into decimal number. Remember now it is 11000011. So let me just take a print screen of that and I'll show you something on PowerPoint. Sorry. Alright, so if we change this into a decimal number, right? So we know that this is 2 to the 1, 2 to the 2, 2 to the 2 to the 3, and 2 to the 4. Right? So it is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. If you have it like this, let's say for instance you have 128, we're going back to that, 64, 32, 16, 8, 4, 2, 1. And we never use, but I use a 0. Hmm? Yeah, man. Any one of them. Any one of them. Any one of them. All right. So right now we have 4 bits right here. So 1, 2, 4, and 8. Right. So we have 1, 2, 3, 4. This is the 8 right here. This is the 4. This is the 2, and this is the 1. Why know that this is a 1? Because anything at all raised to the power of 0 give you 1, don't it? Hello? Hello, 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 hello? Me not hear nobody. People? Body gonna sleep?
Yes,
My phone not working? Okay.
Sorry, hear me?
Yeah?
Sir, I
Yes?
hear me.
Sir, we're not asleep, sir.
You're not
Sorry,
listening?
you could just explain. Could you explain back from the starting, please?
Alright.
I stepped away from the
Okay,
computer.
alright. Look here, so
Sorry.
now. Look here. Remember we were doing some time ago? When we were doing some conversion from binary to
Yes, sir.
decimal? Alright, and we did it in the networking as well. Alright, look here now. We have 4 bits right here so to deal with. So we can use this section of it for the 4 bits. So this would be, remember what we did with the binary? So it's base 2. 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Right? 2 to the 0 always give a 1, don't it? Which is 1 right here, so don't it? 2
Yes,
to
sir.
the 1, 2 to the 1 give you a 2. See the 2 right here? 2 to the 2 give you a 4. See the 4 right here? 2 to the 3 give you 8. See the 8 right here? Now we only have these 2 to work with, which is 2 to the 3 and 2 to the 4. 2 to the 3 and 2 to the 4. This is 8 and this is 4. So that is 12, don't it? So right here, so is 12. This and this give you 12, don't it?
Yes, sir.
Alright, so we know say a 12 don't it, so. What about this right here? So these 2 turn on. So this is 2 to the 1, no 2 to the 0, which give you 1, and 2 to the 1, which give you 2. So that is 3. Twelve minus 3 give you how much? What does 12 minus 3 give you? What does 12 minus 3 give you? 9? Don't it? Hello?
Yes.
Alright.
Sir, you're not hearing me, sir.
Go on again?
You're not hearing me?
Yeah, man, I just hear in a little while. So we know that this is 12 up here, all of this is 12, don't it? And all of this down here, so it's 3. So 12 minus 3 give you 9, don't it? Look how we're gonna get 9 back down here, so cause this is the answer now, you know. This is 2 to the 0, which give you 1, don't it? This is 2 to the 0, this third on, a bit here third on, 2 to the 0, this is 1. See the 1 right here? This right here says 2 is 2 to the 3, which is 8, don't it? Don't it, people?
Yes, sir.
2 to the 3, which is 8. It's not writing properly. Yeah. 2 to the 3, which is 8. So it is 8 plus the 1 here. Is how much? No 9?
Yes, sir.
Right. So this is another way how you can do it. Alright. So now that you understand that, make us say we can move on because time ago. So that's all she does right there. But she does do it straight like this. So if you don't want to use the carry and the barrow, then you can do it like this and you bring it back down here so like this and you get it back like this. 1 0 0 1. Alright? So let us go now to what she was doing now before. Back to the classroom. Subtractor. Alright. So this is what goes on right here. Right? 0 minus 0 is 0. You don't borrow nothing. 0 minus 1. See it? This is the trick right here, so is what this is the only time when you put on the 1 and borrow. When the 0 is in front. 0 minus 1 is 1, but you borrow 1. Alright? 1 minus 0 is 1. You no borrow nothing. 1 minus 1 is 0. Still no borrow nothing. You must always look out for this one right here, so. This is the trick one. So we're gonna draw the K map now. And the K map now, we're gonna draw the K map for the difference and the K map for the borrow.
So now I'm considering my K map for difference. So how many variable K map we need to consider? That will be depends upon the number.
Alright, how many variable K map we want? How many input variable do we have, people? We have 2 input variable and we have 2 output variable.
Sir.
And we have 2 output variable. Alright.
Number of input variables. See here, the number of input variables here is 2. So you need.
So it is 2 to the 2. And 2 to the 2 give you how much? 4.
To consider 2 input K map here. So I am just considering 2 input K map here. So that 2 input K map containing A and B. So which is having 4 cells, totally 4 cells. So for a 2 variable K map, you can observe 2 square cells. That means 4 cells. So now here in this K map for difference, where you need to put ones means wherever you are having ones in this column, there you need to put 1.
Alright, so somebody go ahead and fill in this. So we're gonna use these 2. So we're gonna use this and this. And then we're gonna come back, draw another K map, and we're gonna use this alone. So we're gonna use these 2. So we have A, B, so it's not A and B. So what you're supposed to have? Not A and B, don't it?
Yes, sir.
Alright, so let me just see if I can copy this again.
So you can't crop out your hand. Can't crop out your hand.
Yeah, man, you can't crop out. And can't crop out. It not go thing there. I want to just put in the K map and we're gonna see what will happen. Alright. So if we look at this right here, so if this is not A and not A, this is not B and not B. Let me just put it on it and you determine. Alright? So we're gonna call this a A and a B. Alright, so when it says B, when it says A, this is a not A, which is 0, and this is A down here. This is a not B, and this is a B. If we look what we have right here, so we have a not A and a B, don't it? Where's the not A and a B? Right here, don't? See not A and the B? Which is right here, don't it? Hello?
Yes.
Alright, so we want a A and a not B now. I want a A and a not B. Alright? What type of circuit that look like? What type of gate?
Yeah.
Eh? The one
Zar.
ZAR. Right away, you know, so that you know it's a ZAR gate you deal with. Right? And usually the expression for a ZAR gate is this. Let me tell you for now. You're going to have not A, B, not A and B, or A, not B. Anytime I tell us something like this, people, anytime I tell us something like this is a ZAR gate. As long as this is something, an expression like this, is a ZAR gate. Hello? So if I am to draw this, as a circuit, I can draw it straight as a ZAR gate, or I can do it like this. So this is A, this is B, and we know that we have an AND gate right here and an AND gate right here with an OR gate, right? Right away we know that is a two input OR gate. And we know, alright, hold on, that's too close. We're gonna draw the AND gate then first. So right away we know that we have two AND gate, A and B. So we're gonna draw the two AND gate first. No sir, we have two AND gate, don't it people? I call this,
Yes, sir.
and make it look prettier. It never look too good. It look a little better now. Alright. So this is a not A for another gate. So we're gonna put a not right here. Not A and B. Note it? And next one is A and not B. Everybody see that? But we have a R right here, don't it? We have a R, don't it? Two of them going at two in that. So this is this one, which is this one. So we're gonna call this gate, the expression for this gate, not A and B. And this one is A, not B. A and not B. But both of them go into a R gate, don't it? See the R gate right here? So is that this or this? So is that this or this? So is it that this or this? So this is how it would look. As well as you can just do it like this. Because we know that this is equivalent of a ZAR gate. We just do this. Come on. Oops. It is. So, bam, 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 bam. A, B. And this is X or so all of this right here is equivalent for this. So instead of drawing these two AND gate right here, so with the two nuts on it and the R, we just draw it like this. Everybody get that? Hello? Hello, hello, hello.
Yes, sir.
Okay. Everybody understand? Is it that you draw it like this or you draw it like this? But this is the expression for it. This is the KMAP for it. Alright. So let me just go back now to the video so that you can watch the video for it. So the video for it now is this one. So you're gonna go through this now.
There you need to put ones. So here I am having 1. Where this 1 came means A equal to 0, B equal to 1. That means A equal to 0, B equal to 1 case you are having 1. So here you are having 0, 1 and 0, 1 for both AB. When A equal to 0, B equal to 1 means here, and now another one is there at A equal to 1, B equal to 0. A equal to 1, B equal to 0 means here. So here you can do diagonal grouping. As I told you, if total diagonal is covered by grouping, then you can take that as XR of that variables. That means you can take this as D is equal to A XR B if diagonal grouping is there.
Hold on, let me just go back to this. Right. So this is XR, or you can write it like this. You can write as A ZAR B. A ZAR B. This is how you write out this, right?
If you are not sure about this diagonal grouping, you can group individually and you can take the addition of that individual prime implicants. So by solving that expression also you are going to get the same XR. So here D is equal to A XR B. So this is the expression came from the K-map of difference. In the same way, we are going to consider K-map for borrow. So now I am going to consider K-map for borrow. K-map for borrow. So this is also a 2 variable K-map because this borrow is also obtained from this input variables. So here I am considering same input variables A and B with combinations 0, 1 and 0, 1. These are the possibilities of A and B individually. So now see where you are having 1 in borrow place.
Hold on, look, Miss Student. Hello? Hello? Yes, Boogie. Me there work. No, me there in a class right now. I teach. No, I'm supposed to up the man. Oh yeah, man, yeah, alright, yeah. Yeah, sorry about that. Look like I have some technical difficulty. Look like it's on my side. So let me just continue where we left off. Are we still there? Hello? Okay.
So only one is there in borrow. That means borrow is coming only once when you take in two input variables. Where means when a equal to 0, borrow is coming only once when you take in two input variables. Where means when a equal to 0, b is equal to 1 in a minus b case. So that's why when a equal to 0 and b is equal to 1 place, I am putting 1, I am going to put 1. So here this is 1 and we are not having any ones to group with this one. So I am taking individual grouping of this one. This is one and only prime implicant in this K map. The value of this individual one will reflect the equation for borrow. So now the equation for this single prime implicant is, so sidewise it is covering 0, that 0 represents A, means A bar. So 0 in sum of products means that is complement of variable. So here A bar top wise it is covering 1 means B. So here borrow is equal to A bar B. So by using these two K maps, we came to know that the difference is equivalent to A XOR B, that means XOR of inputs, and borrow is equal to A bar into B. The only difference between half subtractor and half adder is, in case of half adder you are having we are having borrow, that borrow, in using these two I am taking two input lines. So A and B I am considering. So here for A I am taking complement also. We can say this is A bar line, because as I take in inverter here, this will become A bar line. I am taking B here, this is B line. So these two are input variables and complement of A we require. So here to make the difference, you need to consider XOR of A and B. You need to consider XOR of A and B means you need to consider XOR gate in between A and B. So now you are getting difference here. Now to get the borrow, what you are doing is you are considering A bar into B. That means you need a AND gate. This AND gate output is your borrow. So this is a half subtractor circuit designed by you by using truth table and K-map. So like this you got this circuit. When you heard this half subtractor, definitely you are getting this circuit in your mind. But how this circuit came is, this is the procedure we need to consider to get this logic circuit for half subtractor.
Alright, we're going to look at the full subtractor now. Alright, so we're going to look at the full subtractor now. We're going to use two half subtractor to make a full subtractor. So we're going to look at that right now.
In this class we are going to discuss about full subtractor. By using full subtractor we can perform difference between 3 bits. So initially we are having half subtractor, but by using half subtractor we can perform subtraction between two single bit numbers. If any borrow is occurred to the next bit, then we need to perform the subtraction between 3 bits, then half subtractor is not going to perform that operation. For example, if you are having A like 001 and B like 010, like this if you are having two multi-bit numbers. So here if you want to perform subtraction of B from A, what's going to happen by using half adder means, actually we can use 3 half adders for this, for each corresponding subtraction. And after completing this 1 minus 0, it can be done by the half subtractor. So like 1, 0 minus 1 we need.
Alright, see it here now. This is the trick again, people. This is the only H in this one right here.
To consider 1 with borrow 1. So when third bit came for third half subtractor, it is impossible.
Alright, what gonna be the answer here now? Because this is a 1 now, you know. 1 minus 1. 1 minus 0.
To perform subtraction, so among these 3 bits, that is the limitation of half adder. This particular limitation can be overcome by this full subtractor. So see here, full subtractor is a combinational circuit used to perform subtraction among 3 bits. So here you can say this is the block diagram of full subtractor, which is having 2 input bits with a borrow input.
3 input
so
bit.
Here
3 input bit.
These two are the 2 single bit numbers, and here this is borrow in. So totally we are having 3 inputs for a full subtractor. Similarly, we are having 2 outputs for a full subtractor. That 2 outputs may be difference and borrow out. So here, to design this functionality, so we are going to consider truth table to satisfy full subtraction. So here I am taking truth table with 3 input variables with A and B in, borrow in. So totally, as you are having 3 input variables, so in truth table also you need to mention all 3 input variables for that circuit. So here I mentioned all 3 variables. With 3 input variables we may have 8 combinations. That 8 combinations is from 0 to 7. So I consider all possible 8 combinations for these 3 input variables. Now we need to perform the subtraction operation between each combination. So here, when you had borrow in any subtraction, then you need to put borrow 1 in this place. Otherwise, borrow is 0. Here you need to perform every time a minus b, after that result 0. So here the difference is 0 in b out case. Now in the same way, so 0 minus, here in this case, are you hearing any borrow? By considering two cases difference, so here the difference is 0. So here in this case, are you hearing any borrow means no, so just put 0 in b out case. Now in the same way, so 0 minus 0, the difference up to there is 0. After that, the difference is again getting difference with 1, that means 0 minus 1. When you are having 0 minus 1, your difference.
We're supposed to have for that, people. When you have 0 minus 1, we're supposed to have. Hello?
Sir, what is that 0 minus 1 you're supposed to take from? Say subtract, and add 1, and then the 1 minus 1 would equals 0.
Alright, so what's supposed to be out here now? What's supposed to be out here? 0 minus 0 is 0. Right? 0 minus 1 is what?
It's 1.
You're gonna have in a barrel? You're gonna have in a barrel?
0 is borrow. You borrow 1, sir.
Okay.
Is 1 and your borrow is 1. So here difference is 1 and borrow is 1. So now
everything is okay except when I reach down here so again. I'm going to fuck it different because 1 minus 0 is 1. 1 minus 1, so 1 minus 1 is going to be like up here. So this is the only case we're supposed to have that. And down here as well, 1 minus 1 is 0, and 0 minus 0. 0 minus 1 is 1. Borrow 1. So that's gonna be different.
Here 0 1 0 is there. 0 1 0 means first you need to consider 0 minus 1. In this 0 minus 1, you are different. Whenever 0 minus 1 we are doing, you are getting
0 and borrow. Gonna borrow, so the 1 and borrow. Difference 1, borrow 1.
Getting difference 1 and borrow 1. So that borrow you just mention here, this difference, whatever difference is there, that you just make in your mind, and after completing next subtraction you just put the difference. So after doing 0 minus 1, you are having your difference 1 and borrow 1. When you had borrow, then definitely you just put borrow there. So after that, this difference again you just subtract with this 0. That means 1 minus 0. 1 minus 0 means you are.
How much are you supposed to get? 1 minus 0 give how much? Hello? What's supposed to be there? 1.
Getting 1 here. So now 0 minus 1, difference is.
We're supposed to get now 0 minus 1. We're supposed to get this. So you're gonna get in a barrel. Alright. See the rule here, people.
Minus 1 and be 1, sir.
Yes, and borrow 1, exactly. You know what I mean? But look here, as long as you have a 0 before the 1, you're gonna borrow 1, and you're gonna have a difference.
Is 1, borrow 1. That difference 1 is again subtracted with this 1. That means you are.
We're supposed to have this, so 1 minus 1. 1 minus 1 is how much?
0 here. So now this case 1 0 0, 1 minus 0 is equivalent to 1. That one again we are subtracting. So 1 minus 0, again you are getting.
So we're supposed to have this now.
1 minus 0 now equal 1 and 1 minus. So 1 1 and
Okay.
1. 1 minus 0, 1. That 1 minus 0 is equivalent to 1.
the
You
one
are
I
not
was about.
hearing any borrow here. So, you are taking borrow as 0. So, here last case, last but one cases. So, here 1 minus 0, you are having difference 1. So, again you are doing 1 minus 1 means difference goes to 0. In any case you are not hearing any borrow means you need to put 0 in borrow place. And here 1 minus 1 you are having 0, 0 minus 0 you are having 0. So, in this case also difference became 0 and borrow you are not hearing any case of subtraction. So, you just put 0 in borrow place. So, see here 1 minus 1 0.
Yeah.
Difference
Sorry
became
about that. Sorry about that. I'll have a here.
So when I have the one in the middle, then can I borrow the one?
No. Alright, when I have a 0 before, like for instance, up here, so, you see 0 before the 1 right here, I have another 0 before the 1 right here again, I see another 1 right up here again. Look at the borrow them, you see them?
Yeah.
When the 0 then they before the 1 them.
Oh, you borrow. But when
Yeah,
there's a one before, you're not about to borrow.
you know borrow. Unless unless you don't say 1 minus 1, they get a 0. You understand? So when you get a 0 right here now, see it? You see this now? Then 0 minus 1. You saw one?
Okay. Yeah.
0 here
Mhm.
and that 0 minus 1 if you take in, then you are getting difference 1 and borrow as 1.
You see it now? Everybody see that?
This should put one this.
1 because
So
1
the minus one.
no man, 1 minus 1 give you a 0, don't it?
Yeah.
No you have a 0 and a 1. 0 minus 1
Yeah.
give you a what? The 1
One.
and the borrow. The difference 1 and borrow, don't it?
Oh,
Because you got 0 there. You got 0 yes or no, you know, because 1 minus 1 is 0. So 0 there, so no. So 0 minus 1 is 1, borrow 1.
So, you completed the subtraction, your required full subtraction procedure among 3 bits. So, after completing this difference and borrow out, you need to consider K maps. Table
So
K
we're gonna
map
speed up the
with
K map.
8 cells.
And we know that is a 3 variable K map, so 2 to the 3 is 8. So you're gonna have A. You're gonna have 8 of them. Alright. Remember now, is it the midterm these cells that you have right here, so the midterm you can put the midterm in them as placeholders. So you always have 0 0 0 1 1 0 1 1. They always go out and come back in. Right? So you have 0 1 2 3 4 5 6 7. Right? I know that you can change these 0 and 1 into A. This is a not A, this is a A. This is a not B, this is a not B in. This is a not B, this is a B in. This is a B and a B in. This is a B and a not B in.
So, here A is equal to 0, B in is equal to 0, 1 means, so here you are having 1. And then
So
another,
you know to fill out the K map already, so we can go further now, don't it? You know to put them in already.
I don't know many whatever in the day, but alright, yes.
So how many Zargate you gonna have right here, so? 2 Zargate, don't it? You don't remember how to use this to fill out this? Cancel this section first, and then cancel this section. You know how you get this right here, so? Look at that one here first. Not A, not B, but you have a B in. So look for a not A and a not B. Where do you find a not A and a not B? With a B in. You're gonna find a not B with a B in. Where do you find a not B with a B in? You find a not B with a B in right here, so don't it? But where is it not A? See it here right here, so? This is not A. Everybody see that? The one here right here, so You can look straight on the K-map and tell it. This is saying A, not B, not B in. A, not B, not B in. Where do we find it? Find it here. So A, not B, not B in. See it? A, not B, not B in. You find that A, not B, not B in. This one right here. So see it? A, not B, not B in, which is this one. Right? So that one would be A, not B, not B in. See it here right here, so? And this one would be what? Not A, B, not B in. 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 And the last one gonna be A, A, B, B in. A, B, B in. See it here? A, B, B in. See it here right here, so? You see it? The A, B and B in. There's no not. So you're gonna get the two diagonal now, which is the 2's are get.
So here and here, this cell becomes the combination cell of A is equal to 1, B, B in is equal to 1, 1. So here you are having 1. See here, total diagonal is covered in this K map. As I told you in the last classes also, if total diagonal is covered, you can take XR of the variables in K map. So this may be is equal to, that means D is equal to, difference is equal to A XR, B XR, B in. So this is the resultant expression from this K map for difference.
So you can have a 3 input ZAR gate, as well as you can have AND gate with it as well. Right?
In the same way, I am going to consider K map for, consider A equal to 0, any quarter possible. So top side, that is equivalent to, and then finally you are taking next prime implicant value with the addition of these two prime implicants. So put variables and their expressions, you need to consider the logic diagram for these output variables. See here, I am going to draw for A because sometimes you are taking A bar in this expression.
So you can watch this video again. I know only it's in the Google Classroom, so you can watch it for the half subtractor and the full subtractor.
I enabled inverter line also. So see here, if how you are getting difference means by taking XR of 3 inputs. So just by taking XR of 3 inputs, you are getting your difference in full subtractor. So how you are getting your borrow out means B, B in, A bar B, A bar B in combination, you need to add with a OR gate. First of all, you need to take AND gate of all this, and after that those AND gate outputs are given to OR gate. So B, B in I am going to draw here. So with AND gate, after that A bar B I am taking. A bar means you need to drag from inverter line A bar and capital B. So now finally A bar B in. A bar means again from here and B in means this line. So all you need to add by using a OR gate. So then you are getting your borrow out from full subtractor. This is the logic circuit you designed for full subtractor using designing steps. So first you need to consider truth table and then K maps. By using expression from K maps, you are going to design.
Alright, so we can go back to the lab now. So we would have known now how to do this part of it now. Draw a full subtractor. Draw the truth table for the subtractor circuit. Write the expression for the full subtractor circuit. So you have all the information to do the lab. You can copy them online and do all kind of thing with them, but make certain that you do these up here with them. Everybody get that? Make certain that you do it in multi-sim circuit diagram. Make certain that you do it in the Tinkercad, and you come in and you construct it on the actual breadboard, so that I can see that it works. I do the documentation for it. All of these down here are easy because you can download all kind of thing and use them back. But when I say to draw subtractor circuit, you're gonna draw it. You're not gonna download it. You can copy and download. You can copy it and draw it. You can draw the truth table for subtractor circuit. You can download it and you can go in Google and Google it. But make sure you draw it and write them in. Don't copy and paste. Write the expression for a full subtractor circuit. So write it out. Don't copy it and paste it. So you're gonna draw. You're not gonna copy and paste. If I want you copy and paste, I would have say copy and paste. Copy and paste the truth table. Copy the expression for a full adder. Copy a logic circuit for using the appropriate grade. Copy the truth table for the expression. I could have used all of those things, don't it? But say draw, don't it? Hello? Hello?
Yes, sir. Hearing you, sir.
Okay, all right. So you can now complete lab 2, lab 1 and 2. So the only thing that we need to do now is to cover lab 3. I'm going to do something else with the with lab 2. So we're gonna have to cover something else to go into lab 2. Yeah. So we have the decoder and the encoder and the multiplex and the demultiplexer to do in the next class, and then we go on to the different various type of flip flop. Set reset flip flop, JK flip flop, the T flip flop and the D flip flop. Right? And so that is it. And then we're gonna design an up down counter with Arduino in Tinkercad. So we're gonna use the Arduino in Tinkercad to design up down counter so that the count numbers go up and count numbers go down. I'm gonna design synchronous counters. We're gonna draw a chance until a state diagram for our counters, and we're gonna draw the timing diagram for the counters. So that is it. I think until we meet again. So somebody never remind me to stop the recording, so I'm gonna stop it.